Okay, it's my pleasure to share the first session of this afternoon of Tuesday of CIE and all the accompanying conferences. And our next speaker will be Martin Ziegler, someone I really do know very well. We are good friends. And he will speak on algorithmic cost, and it's going to be about exact real computation. And he will tell you all about that.
Yes, thank you very much. So, exact real computation is a paradigm that I think it's fair to attribute to Norbert. We discussed this earlier today. I will introduce or remind you of this programming paradigm and why we want to devise algorithmic cost. And this is work in progress. It's not finished yet. So again, let me start with a meta-mathematical warm-up, okay? So when teaching mathematics, usual style is first comes the definition, then the theorem, then the proof, and then examples. And case in point is, for example, Lagrange's theorem about finite subgroups, right? So for every finite group, every subgroup, the cardinality is a divisor of the original group's cardinality. When doing research, the approach is often different. First comes an example, then comes another example, and another example, and then start to realize that this example have something in common, and then try to capture what these examples have in common, try to generalize it, make a proof, then capture the hypothesis that make the proof work, and then comes the theorem. An example for this is, for example, the Mersenne conjecture, right? The Mersenne primes, which of them are prime numbers and which are not, came from these examples. But there's another kind, and maybe call this shaping mathematics or arriving at a mathematical definition. This is where you start with an example, and then you want to generalize the example and state the theorem first, and then try to come up with a proof, and then the definition that makes this work. And this work is of this style. And case in point is maybe Bezout's equality in algebraic geometry, right? You remember in algebra, every polynomial has at most as many roots as its degree, right? And if the field under consideration is algebraically closed, let's say it's complex numbers, then we have equality. Polynomial has as many roots as its degree if we count the roots with suitable multiplicity, right? So how to define the multiplicity? Well, in the one-dimensional case, that's obvious. And what in the higher dimensional case? There's a similar setting called Bezout's inequality. If we have polynomials, several, and then they have at most as many roots, if the number of roots is finite, as the product of the degrees. And we want to have equality, not at most, but equally many in a suitable, let's say, complex projective space. But now how to define multiplicity in this setting? That was a complex endeavor, for example, by Alexandre Grothendieck. So first, we want the theorem to hold that that's equality, and then spend all the efforts to make the definition such that the theorem holds, in this case, the definition for multiplicity of roots in high dimensional case. Yes, the present work is of the similar style. Algorithmic cost in exact real computation. I will recall what exact real computation is in a minute. But first start with what is algorithmic cost? Why do we do this analysis? Then different kinds of programming languages and how exact real computation fits into this classification, difference between mathematical and hardware data type. Then what is exact real computation at all? I will show you some example programs in exact real computation and give an intuitive analysis of their performance, one exponential time, one polynomial time, intuitively, and then we want to make this formal. And this is based on previous work which showed that exact real computation is qualitatively Turing complete for real function. So any function that can be expressed on a Turing machine can also be expressed in exact real computation and vice versa. And we want the theorem to strengthen this polynomial time computable real function on Turing machine or polynomial time cost in ERC and vice versa. That's what we want. And then we craft the definitions to make this work, okay? And yeah, you see the benefit, right? Computable analysis is based on Turing machines historically since it was introduced by Alan Turing. But for practical purposes, Turing machines are terrible, right? Unless you're Arnold Schönhager, who wrote a book on numerics on Turing machines. But for ordinary people, they use imperative programming language like C++. And that's the benefit of ERC, having the same power as Turing machines for real data processing, but much more convenient. And we want to show that it's also polynomial time equivalent. So then I will talk about assigning cost to ERC programs. What are the cost parameters? And if time permits, then I will show you that actually the predictions made by our cost assignments agree with practice implementations in the IRAM C++ library. Okay, algorithmic cost analysis. Let's recall the difference between a program and an algorithm, where an algorithm is an abstraction kind of device before implementing or coding. And similarly is the difference between physical runtime, like this computer runs for 2 hours, 17 minutes, and 12 seconds for the program to terminate, versus an algorithm that has linear, quadratic, cubic, polynomial, or exponential asymptotic cost. And the goal is to predict the overall performance of an algorithm from its local properties. How many operations does it execute? What does each operation cost before and without actually implementing and running the program based on the algorithm, independent of hardware details such as PC clock rate, and asymptotically, that is for infinitely for all input instances, as opposed to benchmark tests, which can only cover finitely many, hopefully relevant, but still only finitely many input cases. And in this cost analysis, there's a trade-off between realistic and simple analysis, right? So for example, simple analysis is simply counting the number of operations. For example, when sorting, you all know optimal sorting, n log n, right? N items, but that only counts the number of comparison and swap operations, comparison-based sorting, like for example, a merge sort. But closer inspection, if we want to sort, for example, integers of n bits each, then the situation becomes more complex depending on the ratio between n, the number of items, and m, the bit length. Then maybe, for example, radix sort is actually better than merge sort. Or, for example, calculating Fibonacci numbers, you know, there's this closed formula, Binet formula, one expression, constant number of operations. But of course, each operation is kind of expensive because it may involve irrational numbers, a golden ratio. So better, more difficult, but more realistic estimate counts maybe the number of integer operations, or even better, the bit cost. So that's algorithmic cost analysis. How about programming languages? Well, there's a kind of a schisma between imperative and declarative programming languages, for example, C versus Lisp. And one major difference is that in C, the programmer, the user, has control over the flow of execution, whereas in Lisp, the program itself determines how to arrive at the solution. So in Lisp, it's hard to get really cost predictions because the user doesn't have control. In C, that's why it's so popular, for example, for embedded computing. The programmer has control over the execution flow and thus can control the running time, for example. Similar difference between high-level and low-level programming, for example, assembler versus OCaml with hardware data type versus abstract data type, like, for example, graphs as basic data type. Another distinction is between discrete data, algebraic data, continuous data discretized, or natively continuous data. So the Boost library for discrete data, Maple, for example, algebraic data like polynomial roots. MATLAB is good for discretized computing with continuous data, and the IRAM library, which underlies or which motivated the exact real computation paradigm, really operates on or has the user pretend that it's operating on continuous data. Of course, it still discretizes things, but the discretization is deliberately hidden, information hiding. And final criterion, Turing completeness. Can the programming language express the same as the Turing machine can or not, qualitatively, and maybe also quantitatively? For example, counter machines are known to be Turing complete, but they are exponentially slower than Turing machines, versus parallel register machine are also Turing complete, but they are exponentially faster than Turing machines. And so I'm specifically looking at the exact real computation paradigm, which has been implemented. I think Norbert was the first, and then follow up by Branimir Lambov and Ziyep in the libraries. I'm going to recall that in a minute. Final recall about hardware versus math data types. So you may remember the computer game Civilization, where the human player, rules the country's development throughout history, and the neighboring countries are governed by basic artificial intelligence at that time. And each neighboring leader is described by some parameters. For example, India is governed by Gandhi, and Gandhi's aggression parameter is initially set very low to 1. And then there's a rule in the game, hard-coded, that when during the course of the game the country adopts democracy, then its aggression level decreases by 2. Now, what happens if you play the game and neighbor to India, and India starts developing democracy? Well, mathematically, 1 decrement by 2 should be -1, even less aggressive. But with a data type of byte, there's a wraparound, right? So then the aggression level blows up to 255, and there's a running gag that Gandhi starts waging war against its neighboring countries. So that's, of course, funny, right? But basically, you see the essence is that programming errors can easily emerge due to the difference between hardware and mathematical data types, because we think in terms of mathematical data types. And so it's easier to write correct code if we have mathematical data types and don't need to worry about the discrepancy between hardware and mathematical data types. And indeed, so with classical C, the user programmer needs to take care of allocating an integer large enough to avoid these wraparounds, maybe manually, More convenient is modern programming language like Java and Python have true mathematical integers, which of course are simulated using an adaptive number of bytes. And in C, we can also have that by using an external GMP library automatically and adaptively at a little cost of performance degrees. Now, when it comes to real numbers, the same phenomenon occurs with floating point numbers. Hardware supports float and double precision, but these have rounding errors, and the rounding errors accumulate and propagate, and the user programmer traditionally needs to take that into account and maybe increase the precision by combining several doubles manually. Modern systems like MATLAB or Ariadne allow for variable precision. So the user programmer says, I want like 1000 bits of precision. That same is supported by MPFR. But here the user needs, again, to take care of the precision and how it decreases through the course of the computation. And I think it was Norbert's idea to have that also taken care of by the system, variable and automatic adaptive precision computation, so that to the user, everything appears as exact real numbers. So equivalent to mathematical real numbers, no rounding errors apparent. Operations are exactly, and in particular, there's also a limit operation, so which means you can compute on irrational numbers, on transcendental numbers exactly. There is a caveat, however, you cannot test for equality. I mean, every numerical scientist knows that. That's numerics 101, right? And indeed, computable analysis can prove that testing for real equality is equivalent to the complement of the halting problem. So put differently, sign tests in exact real computation must be partial. Now, how can we write total programs with these partial tests? Yeah, but let me first recall this. So I already mentioned some libraries that support this. IRAM of Norbert, RealLib, Core 2 library. They're all C++ libraries, and how do they implement transparently to the user this exact automatic precision? Internally, all computations are performed with a finite working precision M, and track, that's the system, tracks the error propagation, the degradation of the result quality. And when then there's a sign test, and it turns out that the precision is not sufficient to determine the sign because the argument is very close to zero, then transparently recalculate everything in higher precision. And if that's still not sufficient, then do it again in even higher precision. So, and that works unless the real number to sign to be determined is zero, right? Then no finite precision will ever suffice. That's why it's a partial test, okay? So this re-execution is kind of violating the imperative C++ paradigm, right? Now the user programmer, when there's a test, then suddenly recalculation occurs, right? That's not what people traditionally expect. And indeed, my students usually take half a year to get used to that suddenly a test can lead to an infinite loop. And I'll say in a minute how to prevent these infinite loops from happening. There's another example when reiteration happens, namely in exact real computation, the output precision is specified. And if during the course of the calculation, it turns out that we cannot meet that output precision requirement, then it starts over again. And there's various ways of starting over again in higher precision. So yeah, as I just said, this is kind of undermining the imperative paradigm of C++, this re-execution, which, yeah, a little bit non-imperative. Right. One way of performing this re-execution is by keeping a record, symbolic record of the user's program's calculation. This is what RealLib and Core2 library does. This is very fast, but it eats up a lot, can easily eat up a lot of memory, storing all these calculations symbolically. And Norbert's approach, therefore, is kind of the opposite. Re-execute the whole user program transparently so that the user program doesn't even notice it's being re-executed in higher precision, which saves a lot of memory. And when implemented suitably, then it will only cost a constant factor in performance to compare to predicting the optimal working precision at the first place. Also, the limit operation, you may remember Specker sequence, which can leave the realm of computable real numbers. So there's a hypothesis, the requirement that the limit operation only works on fast Cauchy limits, fast converging sequences. So now you know the basics of exact real computation. Let's look at some user program and how to write total programs in spite of this comparison being partial. And the trick is to have two comparisons which overlap so that at least one of the two comparisons will always succeed and produce a result. And then these can be compared with the choose operation, which we heard about on the previous talk. And the thing is that this makes things multi-valued, non-deterministic, if you like. So here's, for example, what people in numerics have been known as fuzzy or soft best, which can be expressed using this choose operation. So the choose operation receives two or more comparison with the promise that at least one of them succeeds and returns true. And it will return any index such that the argument is true. So if two arguments are true, then it's non-deterministic which index is returned, and the user program must not depend, well, the output of the user program must not depend on which index is returned by this choose operation. Here you see that there's an overlap. When x is very close to 0, then both tests are true. And in this way, for every x, at least one of the tests hold. So in this way, this is a total operation based on these partial tests. So it's lazy evaluation. A more complex program is integer rounding. So integer rounding cannot be continuous, right? Least integer or largest integer. So it must be multi-valued. So the specification for the problem must already include the multi-valuedness. For example, here, the specification says that the rounding 1/2, right, 0.5, can return 0 or can return 1. So it's multi-valued in the specification. And well, most implementation of exact real computation could easily extract that information, the integer rounding, but from the perspective of a user program, it must not rely on that. So here's an example user program that implements this multi-valued rounding using a loop starting with integer result 0, right? And then repeatedly, let's say we have positive real argument x, repeatedly increment the integer k and decrement the real number, well, subtract 1 from the real number x until the real number becomes close to 0. And again, observe that the choose operation makes sure that in either case, even if the real argument is equal to 0, still one of the two tests succeed and then return that. Now let's try to analyze the cost of that program. Remember, our goal is to define the cost, but intuitively, the number of iterations, loop iteration here will be roughly x, where x is the real number, right? So the cost should be roughly O tilde soft linear x times log x something, polylog x. And in terms of the length of x, this is what a computer scientist would call exponential runtime, right? Remember, usually remember runtime in terms of the length, not in terms of the value. So this would be an exponential time algorithm, and we want our cost measure to define that this should have exponential cost. Here's a different algorithm which has supposed to have polynomial test cost. Basically, the idea is to extract the binary expansion of the real number, but the binary expansion cannot be determined continuously, so we need a different approach, and this approach here is based on the signed digit expansion. So what we do here again, first we normalize the argument x by determining integer j such that x is y times 2 to the j, where y is between 1 and 2. This is the first loop, repeatedly divide by 2 and count how often we have divided. And then comes a loop which extracts the signed binary expansion, which by definition is non-deterministic. And indeed, it can be expressed in this way with such a choose operation, now with 3 arguments and with overlap between them. And intuitively, this program, since each loop iteration divides or multiplies by 2, should have logarithmically many iterations. And the overall cost should be polynomial in the length. And we want to make that rigorous by assigning cost to these 2 programs and to any program in exact real computation. So the first program, exponential cost, second program, polynomial cost. That's our goal, to find the definitions that do that. And yeah, previous work has already shown exact real computation to be Turing complete, among other things, also decidable first order theory and many, formal specification, actually, formal specification and the multi-valued syntax, and then proven that the Turing machine-based computable analysis is as expressive as exact real computation. Any real function expressible in ERC is computable on a Turing machine and vice versa. And we want to strengthen that to polynomial time equivalence. So we have the theorem first, and then want to come up with a definition. Qualitative Turing completeness, now quantitative refinement, equivalent to the complexity theory of real function as introduced by Kerry Ko, again on Turing machines. So our first theorem, and this is in quotes because we don't have the definitions yet, but we want the definitions that every real function with polynomial cost in ERC is computable in polynomial time and vice versa. And to do that, we define abstract bit cost for realism, independence on the input length, that's our first complexity parameter, and that's specific to the numerical setting, right? Also in terms of the output precision. Remember, ERC specifies output precision, not working precision. The working precision is determined along the way. So here's the definition. We say that an ERC program occurs polynomial cost on a specific input with a specific parameter if each of the following 3 is bounded polynomial in these 2 parameters. First, the number of operations executed. So this is a simple cost counting measure, which is, as we know, 2 cores. So we add another condition. Yeah, remember, these are the basic operations of ERC, including the limit operation, the partial real sign test, and this choose multifunction. So the second condition is that the largest intermediate result should be at most polynomially longer than the input results, than the input data, right? So if we run a program with large input, then of course the program should be allotted more time, like in the discrete integer case, right? But now here, n is the length of the real input, and n prime is the length of the intermediate results. And the third condition is that the same should hold for the working precision. The working precision that is sufficient to make all the real sign tests succeed. And yes, so how do we define, by the way, yes, the goal is here to define polynomial time cost. Later work hopefully can refine this to quadratic or cubic cost, but here we're taking this modest course stance of only defining polynomial without further refinement. So how can we define these parameters? Well, counting, that's easy to define, right? Each operation counts as one. The length of the intermediate results is defined inductively, just like in the discrete case when we do calculations with integers. Then, for example, each multiplication of integers can at most double or add the length of the integers being multiplied. Same here by definition for real numbers. Yet the new thing is how to define the intermediate precision, the working precision, and that is now defined by induction backwards, because we start or we end with the output precision P, and then we work our way back up to determine what should be the input precision that makes all this work, including the real sign tests and loss of precision. So to conclude, I talked about algorithmic cost and the analysis about different kinds of programming language, in particular imperative C versus declarative programming language, because ERC kind of blends between those two opposites. Then hardware versus mathematical data types, the goal being to have real numbers as a mathematical data type and hide all the discretization going on beyond that, below that. And that's the exact real computation paradigm as implemented in these libraries. I showed you some user programs, particularly how to write total user programs, although the tests are partial. Gave you examples of intuitive exponential time algorithm and one intuitively polynomial time, and our goal is to make that rigorous. So the kind of refining previous qualitative Turing equivalence to strong to polynomial time Turing equivalence, algorithmic cost in ERC, now with 3 cost parameters, the number of operations executed, but also the length of the arguments and the working precision, which is determined backwards, whereas the length is determined by instruction induction forwards. And this is the end of my talk, unless I have time to show you some experiments. Is it good? So yes, so we've implemented these algorithms, the 2 grounding algorithms in the IRAM library. And so to confirm, show you that there's a agreement between the theoretical prediction and the experiment. Abstract bit cost according to our definition versus actual physical runtime measurements using this version of the IRAM library with backend MPFR and a Ubuntu with a 4 GB RAM on a Intel Broadbell CPU virtual machine. And you see the first version of the rounding multifunction indeed has running time, which is kind of linear in the real argument. So we could process arguments up to like 10 to the 7, which means roughly 10 to the 7 iterations, slow running time, right? But agreement with the prediction. Whereas the other rounding function based on the sign digit, extracting the sign digit expansion, has running time which is roughly proportional to the logarithm of the argument. So basically to the length of the argument. It's a little bit, there's something happening for large arguments. So maybe it's a little bit superlinear, maybe x log x or something. But there's an agreement also IRAM itself comes with the example of the logistic map. So iterating the logistic map is notorious, particularly for R approaching 4 as a chaotic system, which means that small perturbation of the initial value can result in very large perturbation of the result. Well, what is large? The iteration stays within the interval 0 to 1. But yeah, the good thing is that the precision needed grows only linearly with a number of iterations. So here's an experiment. Which precision is necessary to perform how many iterations and get guaranteed output precision 50 bits. And you see that this indeed grows linearly, and the runtime accordingly grows roughly quadratically, because linearly many loop iterations with linearly growing precision means basically quadratic runtime. So we have agreement between the prediction and experiments. And now that's really the end of my talk. Thank you very much for listening.